Welcome to this video about how a particle stops in a gas, and the plan for this video is that I will explain you why this question is so important in particle technology, and then you see how to set up and solve the force balance for this case, which is a little bit easier than in the previous case, and finally we will plot the equation which we derived and take a look at the result, and that's already is for this video. So in many particle gas systems, so not only fluid, but now we specify to a gas, it could be a filter, a cyclone, or mills, especially impact mills for particle crushing. And in these systems, it is essential to estimate how quickly a particle responds to the change in gas velocity after being injected, deflected, or released. So if we have a particle as here and it is surrounded by a gas, the question how fast this particle will stop or adjust to a new velocity is essential in unit operations such as filter, cyclones, or mills. And just to set it a little bit in a bigger picture, so in the previous videos we looked about the forces acting on particles when a particle moves, and then in the previous video we also looked at transient motion, so a particle accelerates or deaccelerates. And then we have mainly two important cases, and the one case is which we discussed in the previous video, and there you have a particle in a fluid, and the question is it will fall down, and how fast does it accelerate? And the second very important question is the question you see here, and this is a particle in gas, and how fast will it adapt to a change in velocity? And for small particle in gases, it is sufficient to consider the velocity with neglecting the gravity and buoyancy. So since we are having or looking at a very small particles, microns or even smaller, we can say, okay, these small particles are not affected by buoyancy and gravity. And the second reason is that all forces and velocities act in the same direction. And the direction we are looking is normally a different one. So the forces we are looking is, I will show it you in the next picture. So if we look at all forces we know so far, we have the gravity, we have the buoyancy, we have the drag, and we have the inertia. And the sum of them should be zero, right? That's the force balance. And if we look now at our case, we would say, okay, the particle is moving in one dimension, and since it's not up or down because it goes into the unit operation, maybe in the cyclone, and then we say, okay, it's a very small particle, so we don't need buoyancy, we don't need gravity, while for settling, which goes in the direction of gravity, of course we consider then the gravity. But here we fly around in any way we would like to fly around, and then we say, okay, the small particle gravity has not to be considered, and then we can make it a one-dimensional case. So we have the velocity, so the particle already has a velocity, it comes into the system with a velocity, and the velocity changes, right? And then we have the inertia and the drag force, and that's it. So now we have to look at drag force and inertia. And drag force is quite easy because drag force is in Stokes regime. Also there we already discussed in the previous video about it. And what you just have to keep in mind is we talk about a very small particle or small particle. And small particle means small Reynolds number, and small Reynolds number is Stokes regime. So we have a very easy equation here for the drag force. And then we have the inertia force, Fma, and this is F. We have m, and here we have a, dv divided by dt. And now we just have to sum up both of this, so this plus this equals 0. And if we rearrange the equation then a little bit, we will get the differential equation dv dt, and then minus 18 viscosity, density of the particle, particle size square, and here's the variable, the velocity, right? Here's the velocity coming from, this comes from here, 3 and 6, 18, and so on. So you just make simply the math and you get this very easy differential equation. And this equation we have to solve now, and to solve this equation, it's quite straightforward. So we take the equation and we simplify it in the first step, because all what you see here is a big term. And we simplify it because all of this is constant. So we say it's a constant a. So dv divided by dt equals minus av. And the next step we have to do now is we have the separation of variables. So we have a dv and a v here, and we have a dt here. So all v's go to the left, all t's go to the right, and a is a constant. So dv divided by v, right? And here we have dt, and this is equal. And then in the next step, we just need to integrate it. So with the integral, dv divided by v, and here we take the constant out of the integral minus a, and then we integrate from 0 over t, and here we integrate over all velocities, and then we will get the solution of this very easy case, and this is the logarithm of the velocity equals minus at plus a constant. So, and that's already it, but this doesn't look very appealing, right? So we we have to work out this equation a little bit more. So first we get rid of this logarithm here. So and then we have v equals exponent minus at plus constant, right? So this is how to get rid of the logarithm, and then we can separate this here by basic math laws, and then we have e to the power minus at multiplied by e to the power c. And then if we say, okay, the velocity at time 0, because velocity is a variable of t, right? So with ongoing time, the velocity changes, and at at time 0, the velocity is the starting velocity v0. And if we assume this, we can rewrite the equation that we say, okay, v0 is this part, and the a we can now insert again, and then we have the final or nearly final equation here, because again this term here can be simplified, and we simplify it by t star, which you should know from a previous video where we already introduced t star, and t star is the vice versa of this expression here. So 18 viscosity below the line, and these two go above the line. And if we look at the variables, at the units, these are the units for the variables here, it would end up with a second. So this is t star is a time, and this is the characteristic stopping time, okay? So, and with this we have a final equation, which is quite easy. So the velocity as a function of time is the starting velocity multiplied e to the power minus t divided by t0. And if you think now, okay, the starting velocity would be 0, so time is 0, we make this 0, then this would be 0, and if this 0, this full term here is 1, and if this full term is 1, the velocity equals the starting velocity. Makes completely sense, right? So a very easy equation to calculate how fast a particle will stop in a gas. So the particle enters a cyclone, how fast would it stop? Or we could also use it to adapt to changes in velocity. And then there is also the stopping distance. So one question is, okay, how much time would a particle need to go from starting velocity to 0 velocity? And the same question is, okay, what is the distance the particle travels in this time? And therefore we take the equation we derived, and basically we need just to integrate it over time, because if you integrate the velocity over time, you get the distance, and also there you will find a standard solution for this equation. And then we have the solution. So the distance a particle travels over time till it stops is the starting velocity. So the higher the starting velocity, of course, the more distance the particle would travel, multiplied by the characteristic stopping time, and then we have 1 minus e, and then we have the same expression here, minus t divided by t star. So this is the second solution, and with this we already solved basically the equations. We have two expressions, one to calculate the stopping velocity, one to calculate the stopping distance. And if you would calculate this for a 50 micrometer water droplet in air, so we have a water droplet. This water droplet comes with a start velocity of 20 meter per second, so quite fast. And then you will see that extremely fast. So after 40 microseconds, this a droplet will reach velocity 0. So because of the small size, it has a high area, surface area, and this means it's extremely fast stopped. And in this 40 or nearly 40 milliseconds, it travels a distance of roughly 150 millimeters. So we are talking here about very, very short times and distances. And this is why very often we neglect these acceleration and deacceleration and directly kick out the transient term. But now you can calculate it also for the case of stopping in gas. So what should you do to maybe train your knowledge a little bit? So what I would really recommend is that you set up the force balance by yourself and solve the equation also for yourself to see if you understood and can follow it. And then I would really recommend that you calculate time and distance needed to stop a 50 micron and a 500 micron particle with a starting velocity 20 meter per second in air. And you could do it for water, then you can compare it to my results, or you can use it for any kind of material. And this is something you could calculate by hand. But then I also would recommend to play around a little bit with the particle size and with the velocities to see these influences and how the result will change. And finally, I would also really recommend to make a Python code, and then you can play around with all the values easily, and you see the full behavior as in the diagram I showed you. Okay, so with this, I hope I could explain you why this question is important in particle technology, because in a lot of unit operations, the question how fast a particle stops in a gas is quite important. I showed you how to set up and solve the force balance, which was in this case quite easy because we only have two forces, the inertia and the drag. And then we plot, basically we solve the force balance, and then we plot the equation and took a small look at the result and saw, okay, it's extremely fast how the particle stops. With this, I would like to thank you, and if you have any questions, just let me know.